Sir, one small request, sir.
Yeah, yeah.
I'm traveling today, 5:30. I'll be leaving the class 5:45. I have to leave to the station for some emergency.
Okay, okay.
Okay, then afterwards I'll go through your content because I'm really interested to listen to your classes, but unavoidable situation, I am want to leave 5:30, sir.
Yeah, it's okay. Like
Ah,
I'll keep the video on the YouTube and then the
ah,
content will be also there.
okay, okay, sir. Thank you, sir.
Okay. Okay. Yeah, hello. Good evening, everyone. So, welcome to the fifth week of interaction session, like for the course of a statistic for biomedical engineer. And here we will discussing about of a statistic that we're going to use in the biomedical aspect and all. And I'm the PMRF scholar at Tiruchirappalli. So till now we have seen the 4 week, like we have introduced the courses that are statistic and then how it's going to apply to the biology and all. Then we have seen the applications also, like where it's going to use, like we have the drugs and all. And then we have seen before jumping into the that is statistics, so we need to have some background. That background will comes from the probability will come. Then we have seen the different types of probability we have seen, like that the descriptive we have seen, or maybe that that we have seen the different types of probability we have seen. And then after we have seen like what is the descriptive statistic, like that mean and then mode and all, and then the mode and all. After that, we have seen the probability distributions. In the distributions also, we have different types of that distributions are there. One is something like we'll call a discrete one. Like here, the data will be in the discretized term, and like for that we have a binomial distributions and then Poisson distributions we have. Then coming forward, so we'll coming forward. So we'll be having a continuous distributions like a continuous probability theory. We'll be having like we have the normal distribution, then the exponential distributions we have, and corresponding to that we have seen the expectation. Then we have seen again seen the what is the difference between the mean and then expectation. Then we have seen the variance. Then inferential statistic, like we have started, like once we'll get to know that, like descriptive statistic and all, then we'll inference, like based upon the probability on a statistic, what we are going to infer whether there is any differences are there or not. Let's say we are going to assume any drugs that should have the efficacy. I'll just check anyone is going to join. Okay, so in the third week it was of more of the probability and the distributions and all. Then the fourth week we came like a central limit theorem, like we slowly jumped into the like a statistic, core statistic. Then we have discussed what is the confidence interval and what is the hypothesis, like we have to make it like whenever we have to make the inference about anything, so we have to make some hypothesis. Like first one will be the assumptions, we can say we have to make it. So in that we have the process are there. We have to follow it up like data collections and all. It will go. Then uh, we have to make the hypothesis, like a first one should be the null hypothesis. Then it should go to alternative hypothesis. Then we have to calculate the value based upon the data that have been given. Before that, making the hypothesis that there should be assumptions, we have to check with the data whether data is done normal or not. If data is not normal, so what we have to do, like we have the different tests are there, and we have to check the number of samples also. We have to check it. If the number of sample is less, so we have to use some certain test. If the number of sample is more, so we have to check for, or we have to apply the some different statistic and all. So that we have to check for that. And then we have taken the p value also. P value, that a p value, it's a corresponding to the probability based upon the test statistic will get it. So they will give the power, or maybe like exact the error that they will try to give. Then after the in this class or in this session, we are going to discuss some small sample test, like it's more of like a t-test we'll discuss, and then we'll discuss what is the power of the test, then type 1 error, type 2 error. These are the all things we have seen in the brief in the previous session, but here we'll be having more on the solving the problem. Like we'll take a random data, so each of the data we'll take it, and we'll solve for the small sample test, then we'll solve for two populations also we'll solve, then we'll solve for like some sort of a correlation coefficients also will solve. After that, we'll see what is the type 1 error, type 2 error, how can we avoid type 1 error, type 2 error, or what is the like combination, or maybe what is the relation between the type 1 and type 2 error, how can we define the power of the test. Okay. So today the whole idea will be like we'll discuss like how the hypothesis that should be started and all. Then we'll solve some problem. Then once we're done with that, so we'll see the chi-square test. Let's say the small sample test will done with the t-test and all. Then we'll check the warrior type 1 error, type 2 error. Then will then when the sample size got increased, let's say for the a small sample we have a that n is equal to that's going to be less than 30. If or that in the most of the cases that samples are size will be more, so we have to move that is the move forward to the other distributions or other tests, like we have the chi-square test we have, then we have the f test as there, then we have the that the Fisher exact test is there. Then after hypothesis test that are going to do for the variance also. Before that, we'll see the for the mean. Then we'll check chi-square test for the different applications. Like first one will be the for the mean. No, first one will check with the homogeneity. Then we'll check with the independence, like independence is there or not. Then the third one will be like when we are going to check with the variance. When we have the two populations and all, so we'll check with the variance. Like it's the formula will come n minus 1 square and s square by something will come. Then we have to see the contingency test. Contingency test is something like if you're going to solve the machine learning problem, will be having the confusion matrix. So a similar way we have to take, and then we'll check with the probability plot. That's we call QQ plot. We have to check with that if that norm that data or any the test is going to be like toward the normal, or that we have the significant. So it's going to be a straight line. So that will going to close to the normal. That QQ plot also will see, and like this is the whole idea. So now we'll come to the what is the element of the test hypothesis. So the idea is to like what are the when we are going to make any inferential, just a minute. So the idea is for the hypothesis, like what are the elements should be there. Like first one, we have to based upon the data before setting up the hypothesis, we have to get to know that what is the sample size number. Sorry for the disturbance, actually. So before going jumping into the making the hypothesis, we have to whether my voice is audible. No? Can anyone confirm?
It's audible.
Yeah. Okay. Thank you. So the idea is to when we are going to do the inferential statistics, so we have to make the hypothesis. Before jumping into the hypothesis, we have to know that which test we are going to apply. So that will be based upon the data normality, like whether the data we have taken from the random sample of population, whether that has been drawn as in like the normal distributions, or whether the data having that is a small sample test or that large sample test. If data is going to be like more than 30, in that case, we have to apply some other tests like ANOVA or maybe that chi-square test and all. If the number of sample is going to be less than 30, in that case, what we have to do, we have to apply the sample test, that is t-test. So once we'll confirm with that, and then we have to check with the whether the data is going to be normal or not. For the normality test, we have different types of tests are there. Let's say we have we are going to check the normality based on some statistic. We have to check it, or once we'll check with the all the what we can say like a pre-statistic conditions and all, then we have to set the hypothesis. So first one will be it's going to be a null hypothesis. That the null hypothesis is something that is a status quo. Status quo is means like something that's already existing. But the thing is that we have to check whether the that value is going to be that much equal to or not. So it's something like that already. And the alternative hypothesis is something that we need or something. Okay. Whenever we are going to take any statistics, so we have first will be the null hypothesis, means there is no difference or something. If the difference is there, so it will say that both the mean for the both populations are same. And alternative is something that we need based upon the enough evidence. We have to tell like, okay, this is the alternative. So based upon the evidence we have, that we are going to say the alternative hypothesis. It means something the complementary of alternative. Then we have to see test statistic. Test statistic again we have to go with the t-test. The statistic will be different. And if we have taken the central limit theorem, so that will become the Z. Or if we have the F test, so then that will become the F. If we have the ANOVA, so in that case we have that is the two or three terms are there, like sum of square error and something is there. Then we have the chi-square test, like chi-square test is there, and Fisher exact test will be there. So based upon that, statistic will change. And again, first one will check with the single mean or single population. Then we'll check with the double mean, like a two population. Then we'll check with for the variance, like based upon the our demand and need, we are going to check it. Then we have to find out what is the rejection reason. Then they will give the level of confidence. Then they will say level of that is the level of confidence that is going to usually 5% or the 1%. It depends where we are going to use it. And that if it is teachers at 5%, so they will say if just 1 minute. Okay. So then after the assumptions is like something the clear statement about any assumption concerning the target population. Something like we have to see like what is the actual target populations and all. Then experiment and calculation for the test statistic. Then we have to calculate the test statistic. We'll do the calculation. Then correspondingly, test calculation will check with the table based upon the what we can say level of significance and the degree of freedom. Then then we are going to say the conclusion whether we are able to whether we are going to reject the null hypothesis or not. Anyway, one more question will be there, like we are not going to anyway accept the like something in the statistic that will discuss like whether we have to accept the null hypothesis or not, because the wording itself is not correct. That we'll see later part. So then we'll make the conclusion. So now the things will be it's going to be reject the null hypothesis with the possible type 1 error, or do not do not reject it like with the possible type 2 error. So can anyone say what is the type 1 error, type 2 error? I think that we have discussed in the last class also. Type 1 error is something we are going to reject. We are going to rejecting the true null hypothesis. Okay, that is the result, and that reality is that it's not is true. It's something there is no difference was there, but we have told like there is a differences are there. So means something we are going to like in that case we are making particular some missing claim or over claiming and all. And the type 2 error is something that that is the H naught is false. What we have done, we didn't done. So it's something we have missed the opportunity. So that will become the type 2 error. So again, the question will be like how both are related, type 1 error and type 2 error. So there is always like type 2 error is more, so there is a chances of type 2 error will be less. So it means type 1 error is actually inversely proportional.
Normally it is true, but we reject.
Yeah. So the thing is that whenever will be when we're going to to reduce the what we can say type 1 error, in that case we'll be becoming very narrow minded, or the narrow reason for the to reject the null hypothesis. In that case, what will happen, that the chances of not going to reject the null hypothesis, it become more, is it?
Sir.
So it's both are interconnected and all. And 1 minus p value is the exact confidence percentage. Let's say they are saying 5% or something like 0.001 came. So this is the probability value. So this is the error probability, or 1 minus p will be 99% of the chance like which we can reject the null hypothesis and all. If it is become like something like they are giving the confidence, if the value of the p is less, it means we have the more confidence that we are going to reject the null hypothesis and all. Okay. So this is the whole idea about like type 1 error and type 2 error. Type 1 error is something like we are not going to reject null hypothesis, but it was true. But the thing is that it's not is the something we are not able to do it like a two terms, but in a different context is there. Then we'll come to about a p-value is going to probability that computed value of the test as a statistic at least as a extreme as a specified value. It's going to be a rejection reason. If we take here, so this is our the normal distribution. So if it is here and here, so this is going to be a rejection region, and this is going to be a acceptance region. So actually the p-value is giving actually a like the like that the extreme value, and they are giving the region of rejection. And statistical hypothesis are the hypothesis that are stated in such a way that we have to evaluate for a population with the using of different statistical technique. So hypothesis is something like we have to tell or we have to infer something about the population or the maybe samples and all. Okay, so if the sample is known and 2 sigma is unknown, sigma is something like the standard deviation. So and so in that case, sample is known and then underlying condition is the Gaussian. When we will talk about the t distribution, so that should be normal distributions like Gaussian the distributions. So in that case, the t will become x minus mu naught by s upon that is going to root n. So it's that we have discussed, and then we'll discuss what is the t and all. After that, what is the steps actually is going to involve? First, to evaluate the data. Like data evaluation is something that we have to check with the normality, whether the data is normal or not. If not, then what is exactly they are following. And we have to check with the whether the number of sample, if it is more or it is less, we have to check it out. And then after we'll see with the other conditions, and also then we have to make the assumption. What is the things like whether the data is normal, so we have to check with the other assumptions also. Once we'll get to know the assumptions and all, we have to state the hypothesis. Let's say for if we talk about the drug, and so like if we have that we have the two drugs, we have to check like whether which drug having more efficacy and all. In that case, we have to decide. So first one is the null hypothesis. We'll say both the drugs have the same effect. So then after alternative will become like both drugs is not having the same effect. So once will one will that once will say the set the hypothesis. So in that case, we have to select the test statistic based upon the number of sample and the data is the normal or not. Then after we'll calculate determine the distribution of the test statistic. We can get the from the table and all will get it. Then we'll tell whether we are going to able to collect or not. Then we're going to make the decision actually. So again, again the decision is something like if T calculated or any statistic calculated greater than of T of table, so we're going to reject the null hypothesis. So Based upon that, we have to make that is the decision. Then we have the level of significance. Alpha is the probability, and in fact, it is the probability of the rejecting the true null hypothesis. Again, the terms is the true null hypothesis and all. Okay. So then we have the calculating type 2 error probability. So one more thing, if it is alpha is the type 1 error, then the type 2 error will not become like a 1 minus alpha. Beta should not become 1 minus alpha. Again, there is a more of discussion about that one. That will see, or maybe you can go through the lecture, you can see why it should not be like, because if alpha plus beta will become 1, so it become 100%. But the thing is that is not the always case. We have the other factors are also going to include. Correct. So that case is not going to always 1 minus alpha or 1 beta. We can say the power of the test. Power is different, or the probability that we are going to accept or reject is going to be different. Because if we say alpha, we have the 5%, so 95 1 minus alpha means 95 will be the type 2 error. No, we can't say no, because the things it depends upon the data and all. No, so that is the thing. But the thing we can say the confidence, the power of the test. So in that case, it will become that close to of that one. After that, we'll be having in the statistic, once we'll set the hypothesis, so we'll have either H naught is equal to mu, or no, like H naught mu of mu naught. That is the one case, there is no much of difference. Second, the H1 or HA means null hypothesis. Either it's not going to be a like same. So we are saying like it's a two-tailed test. If they told no, our calculated mean is greater than dot of this one, so that will become right tail test. Like other we can say one tail test. Like here we are specifying whether which mean is the greater than and all, so that we can tell. So again, if we have that two tail test, it will become the upper limit, like that will become that is of mu naught minus get that the z alpha by 2 by into s by that's going to root under n. Upper tail test, it's going to be positive, and the lower it's going to minus. So we can calculate based upon that also. So the power of the test is something like we are going to sell the probability is the probability that the test will correctly lead to the rejection of null hypothesis. It's something whenever we'll say for a particular value sample mean in alternative hypothesis. It's something we have the confidence or power of the test like something, or that in the usually in the statistic, if the power is around 80%, we'll say much good results are there. Okay. So power is actually 1 minus beta. Beta, what is the type 2 error? So type 2 error is not in what you can say exceed going to that's not exceed 20%. It's always the case. You can go to this week lecture, like fifth week lecture, and then you can see like sir have explained that in clear way and all. Okay. So in that case, so the power of the test is something that we have the probability. It's going to be correctly lead the rejection of the null hypothesis. Still, there is a chance of 20% that the error will going to occur. Sometimes we're not going to reject the null hypothesis. And one more thing, like when we'll say H naught, it's going to be null hypothesis, and you should always think like you should always that make sure either we are going to reject the null hypothesis, or we will not say we are going to accept the null hypothesis. How, or can anyone say like why should we like don't dictate like we are going to accept the null hypothesis? Anyone? Whenever in the statistic and all, we are not going to accept the null hypothesis. We'll say we don't have the that is the enough evidence, like so that we are not going to reject the null hypothesis. Okay, we will not tell we are going to accept the hypothesis. Okay, is it correct?
Yes, sir.
So whenever any in the interview or maybe anywhere like in the questions and all, it will come like if we didn't reject it, reject the reject the message, then in that case we should not tell like accepting the hypothesis, accept the, this will become wrong statement. We have to tell, instead of this we have to tell we don't have enough evidence to reject the null hypothesis. If a statistician, if they told we are going to accept the that's going to be null hypothesis, means they are totally wrong. If that we have to tell, we don't have the enough evidence to reject the null hypothesis. It still will not say we have accepted it. Just because of we don't have the that is the enough evidence. So means that the null hypothesis is true. Will not say we have accepted it, because the idea is to, we have to check whether any differences and all, or the things like any differences are there or not. So it's a status quo. I am saying something, there's a differences are there, so there is a complement, like there's a so that so the idea or the ideal case, there's no differences are there. So in that case, we're not going to accept it. Let's say I'm going to buy a bike, and bike two types of one is 1 to 25, or maybe second one is the 150 cc. So 125 have the better mileage, and then that the 150 have the having the lower mileage, because they're giving the more power. So the idea is to, we have to check for that. We'll take different types of the bike. We'll check number of the bikes and we'll check it. So the idea will be the ideal case. Oh, there is no much of or there is no difference between the mileage and all. So it's a status quo. It's an assumption we have make it. But the thing is, we're not going to accept it. We'll tell we don't have the enough evidence to like either to prove it or something, or either we have to reject it, but we're not going to accept it. Acceptance is something in the statistic, like it's very difficult, like especially in the case of a status quo. So now the idea is to, we'll check with the t-test. What is the t-test? Can anyone tell? T-test. T-test is actually is for a small number of sample, is it?
Yes,
And one more assumption is that the distributions of the sample or population should be normal. And one more thing, the population and standard deviation should be unknown. Okay. So this is the actually a assumptions for the t-test. And when the number of sample is going to increase, that in the last session we have seen, like when that the number of sample is going to increase, and so that will become the more or less that it will become the normal distributions. Let's say this is the normal distribution, and this is going to be like the distribution of n less than 30. If that n we are going to increase it, so that's going to replicate or closer to the normal distribution, like in greater than 30, maybe close 100 or something. So they'll follow the normal distributions actually. Okay. So the idea is to, like in that case we'll be having different cases will be there. First one, to check the mean of the random sample, like to test the significance of a mean of random sample of a single population. Okay. So in that case, what will be there? First one is that population should be finite, and that should be like, just 1 minute. So let's say we have the jet test as there. Jet test is like something CLT, central limit theorem. Then we have the t test. That can be, we don't have the bar for the sample. It should be 30. Is it? So population division, it should be like, it should be population is known. But in the case of like there is no like guarantee or like there is no compulsory that population should be have the known. So it can be of unknown also. Standard deviation is going to be unknown. So their test statistic will become z is equal to x minus mu upon sigma. Sigma root under n. Okay. But for this case, it will become t is equal to x minus mu by sigma upon root under n. Okay. So now we'll see. I'll take one page actually. So we'll take first case we have. We are going to check the test significance of a mean random sample. Okay. So first step, we know that when we're going to tell t-test, so we have already made the assumptions and all. So we have to make the hypothesis. So first we have to set the null hypothesis. So that will become h naught is equal to, because it's a that's the one population. So that will become, you know how much x bar is equal to mu. Mu is something that we have given for the population. Then second one will become alternative hypothesis. H1 again will be having two cases. X bar is not equal to mu. This will become two tail test. Then x bar either greater than 1 or less than 1. This will become one tail test. Is it? Then the second step will be test statistic. So t will become x minus mu upon sigma upon root under n, or x minus mu s upon root under n. It depends like where to use. So x is the sample mean, and then mu is the population mean, then s is the sample standard deviation. That we can calculate s is equal to root under summation of x by x minus whole square upon n minus 1. Okay. And then the degree of freedom will become n minus 1. Then after we have to take the decision. How come? Like if we have to calculate given level of confidence alpha, we'll take one more page. And degree of freedom n. So we have to calculate t of alpha n minus 1 will get some value, and t of calculated will get some value. So if t calculated is greater than of t tabulated, we are going to reject the null hypothesis. Okay. If t calculated less than of t tabulated, we are not going to do not reject null hypothesis. Then will not say accept the null hypothesis. We'll say do not reject the null hypothesis. So can we solve some problem based upon this? Like this is the whole idea of this that a single population. Is it clear now? Shall I go ahead?
Yes, sir.
Okay, so we have of 10 individuals are chosen at the random from a population and their height are found to be like this, like 63, 63, 64, 65, 66, 69, 70, 71, 71. It's an inches. Then they are saying like discuss the proposal that a mean height in the universe is the 65 inch. So first step, what will be there? Let's say because the number of sample is already less than 30, so it's going to it's a small sample. And one more thing, like we are going to assume the data is going to be normally distributed. So then we're going to move forward to the second like step that will going to hypothesis. Can you just do it? So we have a x, because for t we need x minus mu upon s upon root n. S will calculate like this: x minus x bar whole square root under n minus 1. Is it? So here we have the n is equal to 10. So first one we have the x. I'll solve also. Parallelly, that you can do also. 63, 63, 64, then 65, 66, 69, 69, 70, 70, 71. Can anyone tell what is the x bar and then s? If you're going to calculate the x bar, that will x minus x bar, and that will become x minus x bar whole square. 63, 63, 3, 3, 6, 6, 4, 10, 5, 15, 21, 29, 30, 39, 40. So that will become 0, 6, 6, 6, 1, 2, 3, 4, 5, 6, 7 into 42. 42 plus 21, 63. 63 plus 4, 67. It's a 670, is it? So x bar will become 670 by 10, it will become 67. So this will become minus 4, minus 4, minus 3, minus 2, minus 1, and 2, 2, 3, 3, 4. This will become 16, 16, 9, 4, 1, 4, 4, 9, 9, 16. So can anyone tell what is the summation came? 16, 19, 35, 16, 16, 32, 32 plus 9, 41, 45, 46, 50, 54, 59, 68 plus 16. It become 84, is it? So that S will become 84 by n minus 1 is equal to 9. So we'll have how much? 3.126. Have you got it? 3.16, 126. I'll take one more page. So we got S is equal to 3.126. X bar we got how much? 67. N we got 10. So now can we calculate? First we'll set the hypothesis. First step, hypothesis. It will be H naught will be mu will be 7 equal to how much they are saying? 65. 65. Okay. Then what will be the alternate hypothesis? It's not going to be a 65. So it become a two-tailed test and take the alpha is equal to 5%. Can anyone tell the t value? Test statistic. X minus mu S upon root under n. What the value came? X bar. It's a 67 minus 65 upon 3.126 into root under 10. Okay. So how much it will come? It's a fundamental question actually. I think it will come 2.02. And the degree of freedom will become 9. So for level of significance 5%, T at 9, 0.05%. How much is the value? Can anyone tell? I'll wait. Anyone? If we check with the table, it will come 2.262. It means now we have to take the decision. T of calculated is come T of tabulated. It means do not reject the null hypothesis. Okay. So is it clear?
Nice, sir.
So can we do one more problem? Here we don't have to calculate actually. We'll go directly. So the idea is they are giving the soap manufacturing company Shop of manufacturer distribute a particular type of brand through a large number of retail shops before a healthy that the advertising campaign. The mean sales per week shop was 140 dozen. After the campaign, sample of 26 was taken, so that will become that the N, and the mean sale were found to be the 147. So dozen with the standard deviation is 16. So can we consider the advertisement is effective or not? It's a E. Effective or not? So given if we take N is equal to 26, it means less than 30. We can go ahead with the T test. And this is a single population. So no issue with that. And the mu is given how much? 140. Okay. And the X bar, it came how much? 147. And then standard deviation came how much? 16. So what will be the null hypothesis? Can anyone tell? H naught will be mu is equal to 1 by 40. And then the question will come, what will be the alternative hypothesis? Can anyone tell what is the alternative hypothesis? Just think about that. Tell me. If you read this effective means effective is something like after the campaign it should increase. It means greater, is it?
Yes.
So it will become mean of greater than of 140. Effective means something that we have the mean already was there. So if we're going to do some campaigning or will do something like for the betterment, it should increase the sale. Na? So in that case, that our after the advertisement, it should increase. It means the mean should be greater than of what was there already. So it's a one tail test. Okay. So what will the degree of freedom? N minus 1, 26 minus 1, it will become 25. So now we have to calculate the test statistic. I'll take one more page. T is equal to x minus mu sigma upon n or s upon n. So x bar we have the 147 minus 140. We have this one 16 into 25. So that will become 7 into 5 by 16. What is the value came? N 26. 2.238. So for the alpha 5% and degree of freedom nu 25, p value what will be there? For one tail, what the value came? If you check with the table, can you please confirm like whether you know like how to see the table, or shall I explain one more? Like shall I explain one time?
Sir, explain please.
Okay. So if you go to the t test table, like table we have to check with the. I'll just show it how to see and all. Here. This is the jet table actually for the jet value, and then the corresponding if for this sometime lower limit of the right 5% tail will be the it's going to 1.64, that the area will that will become that the 94%. And if you go with the 0.5% so it will become 1.2.5. That's a good lower table. Now we'll go, I'll show the t-test. Degree, what was the degree of freedom for us? Degree of freedom was 25, is it? And so in the t-test, we have two things will be there. One, degree of freedom. Then the whether the test is two tail test, or that's going to one tail test. So our case, what was that? Degree of freedom we have the 25, and then test was one. That's going to one tail test. One tail test also how much? 5% was there. So 25, and we'll go here, and then 5% will come here. So what is value? It's going to be a 1.708. Is it? If we have the two tail test, like there's a no tell no whether the that advertisement was effective or not. In that case, 5% will become here for two tail test, and the 25, so it will become 2.060. Is it clearer?
Yes.
Will
So
test once, please.
so the thing is that we have what we can say. I'll take, right. In the case of what we can say, here, in the case of t test, we have what is there. We have the degree of freedom. Then we have what you can say, like t value. No, no, that's the level of significance. So it's alpha. So alpha, again, if we check with that, we have the two cases: two tail test and then one tail. So now we have to get the value of t at degree of freedom and then the level of significance. Okay. So now we have to check the what was the degree of freedom for our problem. We have the degree of freedom of 25, and then alpha is equal to 5%. Like that's going to 1%. In that case, this one we have the 25 here. This is the degree of freedom. So we'll come and going to mark it here. Then when we have the two tail test, if we have the two tail test, so we have to go 5% and will come back here. So it's going to be somewhere here. So this is the case of two tail test. If now for the our case we have the one tail test, 5% alpha. So we'll come back here. So that the T tabulated is the going to be 1.70%. Is it clear?
That's clear.
If let's say two tail test, if the 5% means we have to show that see this, that going to this one, and two tail test 1%, so we'll see this one. So one tail test will become 0.5. Okay. So I think the hopefully that is that is that's going to clear now. Okay. So from the table we got the value of 1.708. So now we have to make the that what we have to make the conclusion. T of calculated is the 2.38. 238. T of tabulated is 1.708. So T calculated having greater than of T tabulated. So we have to reject the null hypothesis. Is it clear?
Yes, sir.
So now we'll go when we have the two populations. So till now, what we have discussed, we have the only one population is there, and we have drawn the mean, and we will not bother about the what we can say standard deviation. Okay, so now we have the population one, population two. We have we'll take some random sample from here x1. We'll take from here x2. So corresponding, it will become x bar, x1 bar, x2 bar, is it? And that sample we take, that should be less than of 30. Is it clear? So first one was, we have the only one population, we have drawn only one sample. Now we have two population, we have drawn two sample. So in that case, we have to check with that. So in that case, what will be the test statistic? In this case, test statistic will become T is equal to x1 minus x2 upon sigma x. What is sigma x? Can anyone tell? T will become x1 minus x2 sigma 1 square n1 plus sigma 2 square by n2. Is it clear? If we're not going to take sigma, so that's going to be s. So that s, how can we calculate? Anyone? The sigma or x. So that sigma s or sigma we can calculate through. For the simple one was there, it was summation of x1 minus x2, x minus x bar. But here it going to be a x1 minus x1 bar plus summation of x2 bar upon n1 plus n2 minus 2. So this is the formula for standard deviation actually. Okay. So once you calculate the t value, then the procedure will be same. Then we have to that first to test the hypothesis. Like now, first to set the hypothesis. What will be the null hypothesis? Then what is the alternative hypothesis? Then we'll calculate the t like a test statistic. Then we'll going to get the value from where table. Then we'll compare and then we'll make the decision. Okay. So based upon that, we have the one value. I think. Shall we solve or is it clear? I can go ahead because we have to discuss some chi-square test and then some problem for the previous session also. Shall we solve one problem here? Uh-huh.
One problem will solve here, sir. Then we'll proceed.
Yeah. Okay. So everything is same. Only thing the formula for that is x t got changed. X1 minus that x bar 1 minus that x2 bar. Then this got changed. Everything is going to be same. That we have to calculate the t statistic. Then we have to get from the value from the t table. Then we'll compare whether if it is going to get that greater than the table, we are going to reject the null hypothesis. Otherwise, we have that will not going to reject the null hypothesis if it's the second case. So we have the one diet A plan, like we have the two population for the diet A and second population we have the diet B. From here we have took some value, from diet B we have took some value. So now the idea will be to calculate the x1 bar, x2 bar, then S, then with T statistic and all. Can you start doing? I will also start that panel. I will do. So can you tell the x1 bar, then x2 bar? Just tell. Sure. Because the N1 will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. N2 will be going to be a 12, 3, 15. So we'll take first diet A. X1 will be okay. Then we have the diet B. X2 x1 minus x2 bar x1 minus x2 bar whole square. Can anyone tell? We have the value of 25, 32, 30, and it will go till 25. So summation of it will become, I have the value, so I'll just keep it 336. It will become 28, and this will become 450 by 15, it will become 30. Okay, or shall I do the full problem? Like, shall I solve each and every step?
Yes.
That the full step, or like, or I just keep the value? I think if you get some time, so you can go through the steps. The steps will be same. The formula that is going related to this, I have to, because I'll give that give the value now. Okay.
Yes. I see.
So the formula, I'll take one page actually. So we have S is equal to summation of x1 minus x1 bar whole square plus summation of x2 minus x2 bar whole square, all n1 plus n2 minus 2. It's going to be from here full. So I'll give the value. So this summation is going to be how much? 380. It's going to be 1410. That should be 380. So we'll solve now. 380, 1410. Just note down the value. If you are going to solve later parts, you can practice it. So that will become 8.46. So now test a statistic will be x1 minus x2 bar. Okay, because that standard deviation and all that we have to, what will be there? S, it's going to be a root under 1 minus n1 plus 1 minus n2. Is it? Formula is correct now? 28 minus 30 upon 8.46. So if you take up, so n1 n2, so 12 into 50 plus n1 plus n2, 27. So it will become minus of 0.61. So let's say alpha is equal to 5%, and degree of freedom is actually how much? N1 plus N2 minus 2. It become 25, like n1 plus n2 minus 2. So T table again will go. We didn't set the hypothesis now. What are the what was the hypothesis? Hypothesis is that whether the diet 1 and diet 2 having the effective or not. Like we're not saying that one is having more effective. So we'll tell H1 is equal to like mu1 mu2, or maybe the x1 bar is equal to x2 bar. Okay. So alternate will be x1 bar is not going to be a x2 bar. So now we have to go to the table, and that we have to search at T25 5% two tail test, two tail. So what is the value came? It was 2.062 that we have seen last time. I showed. We were having 25 with the 5%, so it become 2.060. Okay. So what we got, T calculated is actually less than of T tabulated. So means do not reject the. Similarly, the things you can do also now. Like I think it's clear now. Any doubt is there in this? No, as such. No, no.
No, sir.
Okay. So the second problem is there that I'll keep in that so we can solve later part. It's already given like 12% are there resulted in the following conditions and all like there. Then we have to they're saying accompanied by something. So now we'll check that to test the significance of an observed sample relation, or that's going to be correlation. For correlation, that the test statistic will going to change, like how much, how test statistic, like first one will be going to be a null hypothesis H naught. It's going to be a rho is equal to 0, means there is no correlation. No correlation means like that will become the rho, that will become the 0. Then the alternate hypothesis will become H1. There is some correlation are there. So there is a case of the two tail test only. So here the test statistic, here the test statistic will become T is equal to R root under 1 minus R square root under n minus 2, and the degree of freedom will become n minus 2. Okay. So the idea will be like we'll be having either we have to get the correlation coefficient value. That we have the formula that will solve the problem is there, and the t will get the value, and the similar case now we'll go with the we'll get n minus 2 is the we have what we can say degree of freedom, and we have that t calculated, and we have at the given significance level we'll get the value from the t table, and then we'll compare it. So now we have the one problem is there, a random sample of pair 27, so n they have given 27. Okay. Then rho, if they have given 0.42. So the idea will become they have told already normal population, so we don't have to think too much. Now they are saying if that variation is population is going to be uncorrelated. So first step H means it's going to be null hypothesis. Rho is going to be a like uncorrelated means there is no correlation. Is it? Uncorrelation means there will be going to be a no correlation. What will be the alternate that the hypothesis? It become rho is equal to 1, is it? And correlation coefficient R is given 0.42. Okay. So now T will calculate R upon 1 minus R square into n minus 2. 0.42 into 25 upon 1 minus R square will become 1 minus 0.42 whole square. So it will come 2.31. And n will become, no, degree of freedom will become n minus 2 mu. So it will come 25. So if you calculate the table at 5% coefficient level, that's going to level of significance. In that case, that what is the t value will come? 2.2 till test 5%, 0.60. Now we have seen t calculated is greater than of t tabulated. So we are going to reject the null hypothesis. Okay. So with this, I think we have done with the t-test. There is no more cases and all are there. So now the idea will shift to where? Now the idea is going to shift to the when the sample is going to be large, means n greater than 30. Till here, any doubt is there? Anyone? No one is there?
Okay, clear, sir.
Okay. So before jumping to the F test, we'll see the T test actually.
Yes, sir, understood.
Yeah. Thank you. So till now we have done with the t-test. T-test we have seen the 3 to 4 type of problem we have seen. That we have the one more type was there when the differences were given, then how can we calculate and all. Like it's a differences in the mean populations and all. It's a special case of the what we have seen for two population variations and all. So I don't think like we have discussed and all. So now once we have seen with the when the number of sample is less and then the normally distributor is there, but when the things number sample got increased, so what will be the case? Like in that we have to apply some other test and all. So we have the chi-square test. In that case, we don't need the like data should be a normal distributions and all. It's going to be like skewed either side, and it's going to be either like it's a positive side. It's going to be skewed all that's going to always. Why? Because that if it's going to skew negative side means that the probability will become a negative, so that is not going to correct. So it's going to skewed always the positive side. If whatever the narrow side will become, if that alpha region will become the lower, so means we have the good chances of to we are going to reject the null hypothesis. But the chances of the error will become type 2 error will become more. Okay. So the idea will be to actually to confidence interval for the variance. Earlier we have checked for the population mean and all. We have checked on differences. We have checked on the correlation. But but sometime what will happen, because when we see the statistic, so we might be not able to see the differences when the mean is there. But and in the population, if the variance is more, variance means differentiation between the population or sample is more, what will happen that the whole distribution is going to be changed out. So in the statistic, we should not trust only the mean. We have to think about what is the spread. Spread means what is the distribution of the differences at all. So in that case, we have to check with the some other tests like we have the chi-square test. We have the ANOVA test is also there. Actually, for the analysis that is going to ANOVA, like it's a analysis of the variance. So in that case also, if the for the ANOVA, we have to like tell like whether the data is going to normal. If data is not going to normal, then what will the case? In that case, we have the what we can say chi-square test. Chi-square test is actually also till the n greater than 50 and all. We have to see if and in that say, so we are going to say compare a set of actual frequency with expected frequency, that how a well a sample fit a theoretical distribution is a goodness fit or it's something we'll be saying that we have the characteristic we have to fit to the any particular distributions. Let's say we have the one data samples are there x y x either x1 x2 x3 and xn. So we have to fit to the any particular distribution for a like some like a binomial distribution, maybe the polynomial distribution. So actually, the chi-square test is actually used for the homogeneity, independence test, or the fitness of the test. Fitness test, we can also say we are going to fit for the particular. And in the last case, we'll check with the single variance also, like how it vary with the single variance and all. Okay, so that area of the area under the curve is going to be 0, and the area under the curve between the 0 to chi-square value is a cumulative property, and that should be always should be the which side? Positive side, like this. It will not go this side. Always we can have seen here. Why? Because they are showing the overall cumulative properties and all. So it's not going to be a negative side. Always. So what is the assumptions and all in this case? N should be more than 30. Sometime we'll be knowing that standard deviations also, and data need not to be normal. So if we talk about the what is the application of the chi-square test, first one is that independence of the attribute. Independence attributes. Second one will be to check with the what is the chi-square test fitness, and the third one will be the variance. Okay, so the chi-square test is a measure of how far the observed count are expected count. It means how far. It's mean giving the variance. Is it? It means they are giving the spread. Is it? And one more thing, the formula for that the chi-square statistic. Chi-square statistic, like for the t-test, what was that? T-test we were having x minus mu upon sigma upon root under n. But here we'll be having chi-square equal to observed minus expected by square by expected. So in that condition will be total number of frequency should be the large sample, like it's going to n greater than of 50, and summation of observed frequency and expected frequency should be equal. No expected frequency should be the less than of 5. Again, we'll solve the problem. And no information about the parent population, whether the population is normal distributions, parametric, non-parametric, and all. That can be of anything. We don't have any info about that one. Okay. So I think the chi-square test is clear. Actually, is for the variance. Variance means how data are spread from the expected count. Okay. So how actual spread of the population or the sample is. Okay. So now we'll check for the first what is the chi-square test for the independence of the test. How we'll do it? Can anyone tell? We'll take some problem and we'll check whether the discuss the usefulness of the quinine in the check-in of the malaria. How come? Like before that, we'll check chi-square test. We'll check with the chi-square test for the independence of the attribute. How come? Attribute, can anyone tell? What do you mean by attributes? Attributes is something we have the property. Is it?
Yes, sir.
So in that case, first thing we have to set the hypothesis. I thought of solving the problem, but we'll explain you how it going to solve. H naught and the variance that should be first case will be there is no differences are there. Then second one we'll check like we'll say the variance s square. Then after chi square we have the chi square summation of observed minus expected f e. It's a summation of whole actually. This become the chi-square statistic and then degree of freedom is will become n minus 2, is it? And level of significance is alpha. So we'll get chi-square test, we'll get the value from the calculation. Then from the chi-square we'll get from the table. Then we are going to again check with the whether it's going to be good enough or no. So can we go ahead? So that before that we'll be having a what we can say contingency table. I think one topic was there contingency table to find out the to find out the what to find out the value of expected frequency. Observed will be having the already idea. Let's say we have that 2 by 2 contingency table. We'll solve. It's going to be A B C D. Either I will take one more page. Just 1 minute. 2 by 2. So A B C D, that will become the row total. A plus B C plus D, and this will become the column total. This will become A plus C and B plus D. Let's say we have the observed frequency FO and FE expected frequency. For the A, we have the A, B, C, D. So for expected frequency, it will become E of A, E of B, E of C, E of D. Okay. So the things will be like how it will go. How will get it the expected frequency of A? Can anyone tell? The formula for the E is row total into column total become by grand total. It will become N actually. So what will be the expected frequency of A? Can anyone tell? How come? It's going to be for A, row total is A plus B, and for A, it become A plus C upon how much? N. This is going to be grand total. N, like A plus B plus C plus D. Okay. E of B is similar for B. A plus B and B plus D by N. And E of C will become A plus C into C becomes C plus D upon N. E of D will become row total will become C plus D, column total will become B plus D by N. So this is the whole idea, and the degree of freedom will become R minus 1 into C minus 1. R is that equal to number of row, C also number of row. Okay. So I think that the chi-square test for the independence, I think it's clear. Now we'll solve one problem based upon this. Okay. So we have a one in anti-material campaign in a certain area. Quinine was administered to 12 people out of total population 3248. Then the number of liver cases is shown in below. Discuss the usefulness of the quinine in the checking of the malaria. Can anyone tell like what is the null hypothesis? Can anyone tell? Just 1 minute. Please solve. I will restrict.
You're calling is
Uh, what will be the what we can say null hypothesis? Can anyone tell? There is no correlation quinine and malaria. Alternative will become there is a relation. So now we'll make the contingency table. We have the treatment, fever, no fever, quinine, then no quinine. I'll take one page. VH have 20, 220, 782, 2216. 2216. Row total will become 812, 2436. Column total will become how much? 240 and 3008. So total we have a 3298. So can we calculate the heat fever? Like 20. 812 into 240 upon 3298. 792. It will become 892 3008 3298. E of 220. 240 into 2436.3298. It will come some answer. E of 2216 will become 2436 into 3008 upon 398. So we have to create a one table actually. I will create one. What's time now? We have the FO, then we have the FE. FO was the 20, 792, 220, 2216. For corresponding expected frequency, it to E20, I think it's a 60. Just you can calculate actually. 752 and then 180 and it become 2256. So this is actually 60, 752, 180, 180, 2256. So FO minus FE will become minus 40, 40 and 40 minus 40. So square of FO FE whole square will become 1600, all 1600. So now FO upon FE whole square upon FE. How much it will become? 1600 by 40. How much? 60 actually. No, sorry. It will become 26.6. 1600 by 752. It will become 2.12. 1600 by 180 will become 8.88 and 1600 by 2256 will become 0.70. So now summation of FO minus FE whole square upon FE will become 38.37. So now chi square will become summation of FO FE square upon FE. It came how much? 38.37. Now degree of freedom R minus 1, C minus 1. How much it will become? 2 minus 1. 2 minus 1 become 1. Level of significance is equal to 5%. So calculated one we have how much? 38.37. Now tabulated 0.05 and of 1. How much is the value? We can go to the chi-square table. We can go to the chi-square table. F distributions. F. F. This is the chi-square table. 1. 5.5% of the level, degree of freedom 1. So it become a 3.841. So this value. Okay. So we'll go back and we got the value of 3.841. So actually 3x calculated is actually of tabulated. So we are going to reject the null hypothesis. Is it clear? Can anyone tell? Is it okay now?
Yes.
So shall we go ahead? Next one.
Yes.
So the next idea will be to goodness of the fit for the uniform distributions or goodness of the fit for the what you can say of binomial distributions or maybe the Poisson's distributions and all will be there. In that case, expected value will be we have to apply the word. They will be saying like we have to apply different sampling technique are there while investigating the same group. Actually, the same problem. We can get the X contingency table of 3, then 3 by 3 contingency table will get, and then we can apply. Okay, so and I'll talk about the for the binomial fit. So we all know that expected value will become what? Can you tell? We know the value of the P. What is the P? NCX. Is it? So expected will become N into P. Is it? Everything is same. What we have done for the chi-square will be going to be same. Summation of FO, FE whole square upon FE. But the thing is that expected value of to fit the binomial, we have to apply this one. So expected value will become N into NCX P to the power X Q to the power N minus X. So that is the whole idea for the binomial. Similarly for Poisson's, what will become? Expected value N into lambda power X e to the power minus lambda upon lambda factorial. Is it? X factorial. So everything will be same. Only thing the calculation of the expectation will change. Is it correct now? Shall I go ahead or shall I solve some problem? I'll go ahead and then we'll solve some problem like some based upon the that is the probability and all, and type 1 error, type 2 error we'll see. Okay, so now we'll start with the which of the following best describe a p-value in the hypothesis testing. Can you explain? Can you tell? P-value. They are saying which of the option is giving the best idea about the p-value in a hypothesis testing. When I told we have the so this extreme means they are giving the rejection reason. So the probability of the obtaining a result at least as extreme as observed one, assuming that null hypothesis is true. So this option will be correct. Is it okay? And why can't be the first option? Probability that the null hypothesis is true. No, like that null hypothesis and then hypothesis, they are not going to assign the probability. So that statement is wrong. Probability of the making a type 2 error. No. Type 2 error is something like we have to, like we are not talking about that. Like type 2 error, we are not much of telling about the p-value and all. But we'll tell like one type error will increase, so type 2 error will decrease and all. But that is not going to relate it to the p. Because the type 2 error is something called beta. That the probability of the rejecting a null hypothesis when is true. It's something we are talking about the hypothesis. Okay. So it's not going to related to the what? Unrelated to p value. It's actually a we are going to type 2 error is actually failing to reject the null hypothesis. It's a type 2 error actually. But that is not going to be a related to the p value. It's going to be a irrelevant. So that can't be the option. This can't be the option. This can't be the option. So p value is giving the obtaining a result as extreme as the observed one, assuming the null hypothesis is true. Okay. Can you tell about the hypothesis test? A type 2 error occurs if when, like type 2 error when it will occur. Just tell me. When it will occur, the null hypothesis is rejected when it is actually a true. It means it's a correct that statement now. Say type 1 error. The alternative hypothesis is not rejected when it is actually false. We are not bothered about the alternative, like we are not like so we'll not bother about the type 2 error because the type 2 error or type 1 error is mostly related to the null hypothesis, not the alternative hypothesis. Alternative hypothesis is our agenda. Understood? Not a statement and all. Statement is actually a false. Alternative statement is rejected when it is actually true. Again, we are not when we talk about the type 1 error, type 2 error, it is more of related to the null hypothesis, not the alternate hypothesis. Because the alternative, either we're going to reject it, either we're going to accept it. It's something like we'll tell based upon the evidence, but we'll not going to relate to the type 2 error now. So, null hypothesis is not rejected. It's something missing the opportunity, missed the detection, missing detection. Type 1 is actually a false alarm. Okay. So the fourth option will be the correct. This can't be, this can't be, this can't be. So type 1 error is actually a rejecting the true null. Means it's a false alarm. Type 2 error, not rejecting the false null. It's going to miss the detection. So type 2 error, low sensitivity, it failed to detect the real effect. Reducing the beta is actually required large sample or higher power. Okay. Now we have the third question. Power of the hypothesis test is defined as. Can anyone explain what is that exactly? The probability of rejecting the null hypothesis when it is false. Power is something they are giving the confidence, something like they are going to reject the null hypothesis when it is the false. So it's the correct one, power. Probability of the failing to reject the null hypothesis that is when it is true. It's a correct decision. Probability of the failing to reject that null hypothesis when it is true, it means it's a correct decision. It's not talking about the power and all. Not an error or power. Okay. So that can't be the option. The probability of the making a type 1 error. No, it can't be now. That's the alpha. That the significance label, not the power. Okay. The probability of the obtaining a result that supports the alternate again, whenever we are going to say like will not only correct when the null hypothesis is the false. It's again it's not about the this alternative hypothesis is always based upon the data, not the status quo. Okay. So this can't be the option. So first one is the answer. Is it okay now? Or do you have any doubt in this? Shall I go ahead? Okay, I'll go ahead. So power is actually a 1 minus beta. It's not the thing, it's a 1 minus beta. High power, more likely to detect the true effect. Depends on the sample size, effect size, significance level. So goal is to power should be 80%. Okay. Now we have a consider a chi-square test with which degree of freedom is of the freedom is how much? 5. The critical value at zero point 0.1 significance level is 11.07. If you calculated one is 12.05. What is the p value approximately? Can anyone tell? Like degree of freedom they have given 5. Critical value means tabulated one they have given when 0.05 and 5. It's a 11.07. Then chi-square calculated. How much came? 12.5. So means we are going to reject the null hypothesis. That the answer will be between the 0. But we'll check with the 0.01 what is the actual value. So from table 0.015 we'll get the value. How much is the value actually is coming? It's something around that the one case that can be the greater than 0.05. This will able to tell based upon the table. We'll go and check it. We have the 5 and significance level of 0.01, 15.066, 15.086. So it came 15.06. It means this x tabulated at 0.1 is greater than of x calculated. So this can't be the answer. Exactly also can't be the answer. So that the only option we have left out with the 0.01 to 0.05. Why? We have checked the greater than, it can't be greater than of 0.05. It means there is no significant. We have checked with the 0.01. It's coming like it's no significant. Like we have to reject the we have to that we do not have to reject that's going to null hypothesis. So it will be the in between of 0.01 to 0.05. We can see here chi-square given, degree of freedom given, alpha is given, critical value is given. Since 12.5 is so, we have to reject the null hypothesis at 5%. But at 12.5, for the critical value of the 1%, not significant. So p value will be the always 0.01 to 0.05. I think hopefully this will be the clear. Now we have the next question we have. Which of the following action could increase the likelihood of making a type 2 error? Failing to detect a true effect means missing detection. Okay. How can we do it? I told you that type 2 error is actually inversely proportional to the type 1 error. Means level of significance. So by we can type 2 error risk can be increased when alpha is going to be lower. So it means correct. Increase the sample size, it will give the more precision. So that can't be the answer. Actually, it's going to improve the accuracy. There, that error is not going to increase. Okay, increase the sample size, it's improve the accuracy. Error will reducing the size of effect you are testing for. Obviously, it's going to be increase the error. Increasing the power of test. When we are going to increase the power of test, error will decrease. Okay, so that can't be the option. So I think hopefully this is also clear. So type 2 error risk increases when we are going to alpha, we are going to lower. It will become a strict cutoff, harder to reject the H not. Effect small, harder to detect the difference. Type 2 error is decreased when will decrease. A, error will decrease when we are going to increase the sample size. Power of the test will increase. Okay. So now we'll come to the next question. We have a researcher is comparing two treatment using a null hypothesis test. Using a hypothesis test. The p-value is calculated at 2 be 0.08%. Significance level is set at 0.05. What is the correct conclusion? Tell me. Reject the null hypothesis and conclude the treatment are different. That's not the correct answer, no? Because this 0.08 is greater than 0.05. So means no significant. So this can't be the answer. Accept the null hypothesis and conclude the treatment is identical. I told already, never we are going to accept, will tell like we don't have the, instead will tell fail to reject or not having enough evidence. Okay, so this can't be the answer. Increase the sample size to reduce the p-value. It's going to be latter part, not now. It can't be. Because we already calculated the p-value, we have set the already p-value. So this part will be the latter part. We're going, so that can be done. So correct option, failed to reject the null hypothesis and conclude that there is no enough evidence to suggest a difference. Okay. So D will be the correct option. P-value greater than of 0.08, alpha not significant. Decision is to fail to reject. Interpretation like insufficient evidence of the difference between the treatment. And fail to reject will tell not the prove equal identical. In a statistic, that's a very important terms actually. Now we have the next question. Can anyone tell the what is the next question we have? When interpreting the probability plot, which of the following indicator of non-normality? Can anyone tell? Last question actually missing. When we are going to interpret a probability plot or the QQ plot, which of the following are indicator of the non-normality? Point deviating significant from the straight line. Correct? When they are going to deviate from the straight line, it means it's becoming the non-normal. When they will become the straight line, it's becoming the normal distribution. So this option will be the correct. The presence of the curvature in the plot also again, because if it is normal, it will become the straight line. Let's say maybe here, if it is like this, it's a non-normal. That shape can be a convex or concave. That depends upon the data. So that's this one is going to represent the normal. So B also. Outlier that fall from the rest of the data point. Yeah, because in the non-normal data, outlier will go somewhere. So this option is also correct. It's indicating the data is going to be non-normal. Then point closely following direct straight line. It means they are giving the normality condition. Okay. So this can't be the option. So indicator of the non that good normality in the probability plot will be the large deviation from the straight diagonal line, curved pattern, maybe suggesting skewness or kurtosis, presence of the strong outlier. Indicator of the normality, point closely follow that a diagonal straight line. Then now we have the one more question is there. A study is conducted to test the effectiveness of new drug. The null hypothesis is that the drug has no effect. The alternative hypothesis drug has a positive effect. It means one till test. After conducting the study, researcher find the p-value of 0.03. If the significance level was 0.05, what is the correct decision regarding the null hypothesis? Means uh, calculated p 0.03 is less than of what we set the alpha or p set value 0.005. It means that is significant difference is there. It means we have to reject the null hypothesis and then drug has the significant positive effects. That the first option will be the fail to reject. No, because it's already less than the 0.05. There is not enough. That we do have the enough evidence to suggest the we have the evidence. So that can't be the answer. The result if we can proceed, no, because zero point 0 is less than of 0.05. Okay, so that can't be except again we don't have to accept the null hypothesis. That can't be the correct. So null hypothesis drug has no effect. Alternative hypothesis has the drug have the positive effect. P value is given. Since P value is less than that of alpha, we are going to reject the hypothesis. Conclusion that drug has so a statistically significant positive effect is there. Okay. So now, if the significance level were recorded reduced to the 0.01%, how would you decision the change? Can anyone tell what will be the answer for this. The null hypothesis would be still rejected. We can't say. How come? Previously, P was 0.03% and it becomes so we have rejected the null hypothesis. If we go now, P value is 0.03% greater than that of 0.01%. Here, we were having 0.03 points was less than not that. Now our the alpha become 0.01, but the calculated P is still 0.03. So 0.03 is greater than of 0.01. Okay, so in that case, we can't reject na because so we like fail to reject that the null hypothesis would not be rejected. Yeah, we can't reject na. The result will be same as before. No, the result test need to be reconnected with the reversible. It's again the future direction. Okay, it's the future that directions. Now we have a research using a chi-square test to determine if there is an association between the two categorical variable smoking yes and no. This is the observed frequencies are like this. So what is the expected frequency for the cell corresponding to the smoking yes? Smoking yes. Smoking yes. We need that one. Can anyone tell how can now we'll calculate row total? So 70, 30, 100, 50, 50, 100. Now column total 70, 50, 120, 50, 30, 80. So it become 200. So now to get expected value of smoking yes, and lung diseases yes. Smoking yes, lung diseases yes, 70. So row total 100 into 120 by 200. 60 is the answer. Okay. So I fully so one more last question is there. After calculating the chi-square test statistic, the researcher obtained a value of 6.67. Chi-square calculated is 6.67 and degree of freedom is equal to 1 and alpha is equal to 0.01. So what is the correct conclusion? So now we'll go to the table. We'll find out 1, 0.01. How much is the value will come? 6.35. So x of from table calculated is greater than of x of tabulated. So we have to reject the null hypothesis. There is significant association between smoking and lung disease. Okay, I think shall we wind up?